In this video, we're going to talk about inverse trig functions, and there are going to be two parts to the video. So first part will be review of inverse trig functions, and then we'll talk about taking derivatives. So let's talk about what an inverse trig function is. In particular, we'll look at the inverse sine function. So let's think of it this way. You can say sine of an angle is equal to a number. Arcsine of a number returns to you the angle that has this sine value. In terms of notation, there are a few different ways, or two main different ways to write the arcsine function. So you can write it the long way by saying arcsine x, or equivalently, you can write sine with the -1 on the sine function. And that's also read as arcsine of x, or inverse sine function. So this is not to be confused with something very different. I'll do this part in a different color. So if you write sine x all to the power -1, then you're just saying take the reciprocal of sine x, which you could rewrite as 1 over sine x, which you could also call cosecant x. So let's do a bit of practice with numerical values, the arcsine function. So let's say someone asks you to find arcsine of √3/2. So we would draw our special triangle. We've got that on the side of the screen here. So that's our 1, √3, 2 triangle, where pi/6 is the small angle at the top and pi/3 is the big angle here at the bottom. So if we ask what angle has a sine value of √3/2, that's what we're trying to figure out here, we'd say, well, sine is opposite over hypotenuse. So we'd say, what angle in this triangle here, what angle has opposite over hypotenuse equal to √3/2? That would be this guy. Its opposite is √3, hypotenuse is 2. So arcsine of √3/2 is going to be pi/3. In a similar way, let's erase this part. Let's say someone asks you to find arcsine of 1/2. Then you draw your special triangle again and say, okay, what angle is going to have opposite over hypotenuse equal to 1/2? So that's going to be this guy. So pi/6, its opposite side is 1. So its opposite over hypotenuse is 1/2. And that makes arcsine of 1/2 equal to pi/6. Now, one other handy fact about the arcsine function is that if you put a negative number into the arcsine function, then your angle just becomes negative. So if you say that differently, you can just bring the negative out in front and then multiply that by whatever arcsine of A is. So for example, if you wanted arcsine of negative √3/2, we'd say, well, that's just going to be some negative angle. So we'd bring the negative out in front, and then just as we did above, we'd figure out what is arcsine of √3/2, pi/3. And I would emphasize in this discussion that we've practiced the two different notations for arcsine. So arcsine of √3/2, arcsine of 1/2, written in the two different ways, but in each case, we're just talking about the inverse sine function. So you don't need to know the graph of the arcsine function, but if you are curious, I do have a copy of it in the notes here. It's not necessary to know this in order to take derivatives of the arcsine function. So let's do a little bit of review with the arctan function as well. Will just give us another chance to let these inverse trig functions click in our mind before we get into derivatives. So here's the main idea. We know that if we take tan of some angle, we get a number. And what arctan is going to do is reverse this process. So you're going to put a number into the arctan function, and it's going to return to you the angle that has this number as its tangent value. Now, in terms of notation, just like we said with the arcsine function, there are two different ways, two main ways to write down the arctan function. So you can write in kind of words, arctan x, or you can write in symbols this. So you can put the -1 on the tan. Putting the -1 on a function makes it the inverse function. So you could read this as the inverse tan function. You could say inverse tan of x. So arctan of x, or inverse tan of x, that is not to be confused with something very different. So let's put this other stuff in a different colored box. So completely differently, if you took tan x and raised that whole thing to the power -1, then you're just saying take the reciprocal of tan x. 1 over tan x can also be written as cotangent x. So having the -1 outside the brackets just gives you the reciprocal, versus having the -1 right on the tan function, as we do up here, is what makes it the inverse tangent function. So arctan x, or inverse tan of x, same thing, and we'll practice both pieces of notation. So with that, let's practice some values here. We're going to do 2 little calculations over here. And it would be nice to draw our special triangle so we got something to look at. So we have our 1√3, 2 triangle up here on the screen. Pi over 6 is the small angle, pi over 3 is the big angle. And let's see if we can calculate these values here. So when we're talking about the inverse tan function, the important thing to remember is that tangent is always going to be opposite over adjacent. So if we want to figure out inverse tan of 1 over √3, we're saying what angle has opposite over adjacent equal to 1 over √3? Well, let's take a look at our picture. That would be this angle here. So for pi over 6, the opposite side length is 1. The adjacent side length is √3. So opposite over adjacent would be 1 over √3. So the angle we're looking for would be pi over 6. So in a similar way, let's say we were trying to find arctan of √3. Okay, so this time we're just practicing the other notation for arctan. We're still asking what angle is going to have a tangent value of √3. So we're looking for an angle in our triangle so that opposite over adjacent can be equal to √3. That would be this angle here, because its opposite side is √3 and its adjacent side is 1. So opposite over adjacent is √3 for this particular angle. So that means arctan of √3 is equal to pi over 3. Arctan also has the same nice property as the arcsine function, that if you put a negative number into arctan, that's just going to make your angle negative. So arctan of -a is just equal to negative arctan of a. So let's say someone asks us to find arctan of -1. Okay, well, we're going to need a different special triangle for that. We're going to need the 1, 1, √2 triangle. Both of these small angles here are pi over 4. So in order to compute arctan of -1, well, first thing we're going to say is it's going to be some negative angle. And then second thing we're going to say is let's figure out what arctan of 1 is. So we need to find an angle in this triangle so that opposite over adjacent is equal to 1. So if we use this angle here, that would work. Opposite side length is 1, adjacent side length is 1. So we do get opposite over adjacent equal to 1. Okay, therefore arctan of 1 is equal to pi over 4, and that means arctan of -1 is equal to negative pi over 4. So as we said with the arcsine function, you don't need to know the graph of the arctan function. I put it in the notes, just in case you're curious, but it's not something that you need to know in order to take derivatives of the inverse trig functions. So that was a bit of recap with the arcsine and the arctan functions. There is an arccos function as well, but it's not as useful for applications. So we're going to focus our review just on arcsine and arctan and make sure we're comfortable with those. So next thing we're going to do for our review is just focus on some numerical calculations with our calculator, make sure we're comfortable putting that into the calculator. So here's our function, square root of 4 minus arcsine of 3x minus 8, and we want to find f of 2.8. So we're going to be putting a number into this arcsine function. And remember, what the arcsine function is going to do is it's going to return an angle to you. So let's think about whether we want that angle to be in degrees or radians. Well, if it were in degrees, then we'd have something like 4 minus 27 degrees or something like that. We would have a mismatch in the units. If this were in degrees and this is just a number, then we'd have a mismatch in the units and we wouldn't be able to do the computation. So we want our angle to come out in radians. And for that reason, we're going to use radian mode on our calculator. So we'll make sure that this arcsine number gets spit out in radians, and then we'll be able to do this 4 minus whatever our number is, take the square root, and complete the calculation that way. So that's probably the most important observation to get this calculation done. Okay, so then we can say f of 2.8 is equal to square root of 4 minus arcsine of, well, let's just figure out what 3 times 2.8 minus 8 is. That would be 0.4. Okay, and then as long as our calculator is in radian mode, we can type into our calculator square root of all this stuff. For the sake of the calculator, you would want brackets around everything under the square root, just to make sure that the square root applies to everything there. And then we can type this in just as is. In theory, you wouldn't really need brackets around the arcsine. If you're just putting a single number into an inverse trig function, you don't need brackets. The real brackets that we need for the calculator are the ones that are around all the stuff under the root. Okay, so we can type that in just like that. It should come out to about 1.9. So that's just a little test as to whether we're okay using our calculator to compute inverse trig functions. So let's try one more. F of x is equal to arc cos of all this stuff. Inside the brackets, we have cos 2x over x plus 1. We want to find f of pi over 7. So again, it's going to be important that our calculator is in radian mode. The reason that's important in this problem is because we're going to be putting this angle that is in radians into a trig function. So because of this cos 2x here, we need our calculator to be in radians so that it understands that the angle that's being input is in radians. So we'll say f of pi over 7 is equal to arc cos of all this stuff. And inside the brackets, we're going to have cos of 2 pi over 7. Okay, so I'm going to put brackets around that so that we understand that the cosine is applying to the whole 2 pi over 7. And then that also has to be divided by x plus 1. Well, we're continuing to replace the x with the pi over 7. So that would look like pi over 7 plus 1. If we were just writing this down and trying to keep our answer exact, the brackets that would be necessary here, just really the big brackets here showing that arc cos is applying to all this stuff. But for the sake of the calculator, I'm going to put those brackets in blue. You would want brackets here so that the calculator understands all of 2 pi over 7 is going into the cosine function. You would also want brackets here so that the calculator understands that you want to divide by this entire expression, pi over 7 plus 1. Okay, so if we bracket that way with the 3 sets of brackets, our answer should come out to about 1.1. So what has happened here is that we put some number, specifically this number here, put some number into the arc cos function. And so what the arc cos function is returning to us is an angle. So you could say that's about 1.1 radians. And then if you wanted that number in degrees, then you would multiply by 180 degrees over pi, and that would take you into degrees. So that would be about 64.5 degrees. So as I mentioned on the previous page, the applications we're going to be looking at in this chapter mostly use the arcsine and the arctan function. We won't be talking about arc cos as much, but it was probably good to practice putting it into the calculator just in case it comes up. So that wraps up our review of inverse trig functions, and now we're ready to jump into the derivative part of the discussion. Derivatives of inverse trig functions. There are going to be 3 formulas that will be important for this section. So we're going to start with taking the derivative of arcsine of x. The formula is 1 over the square root of 1 minus x squared. If you take the derivative of arc cos x, you get actually almost the same derivative as the derivative of arcsine x. The only difference is that it's now negative. So derivative of arc sine x is positive, derivative of arc cos x is negative. And then derivative of arctan x, that's a bit nicer to work with. It does not have a square root in it. The derivative of arctan x is 1 over 1 plus x squared. So we're going to practice using those 3 formulas. So we're going to do 8 short examples here just to practice those 3 formulas. Part A, let's find f prime of x for f of x equal arcsine of 7x. Okay, now when you see the function like arcsine of 7x, it might be written like this. It might be written with brackets on it. That's just really personal choice as to which way it's easier for you to read. Okay, so let's jump into our derivative. Well, there's going to be a chain rule involved here. The outside function is the arcsine function. So let's focus on taking the derivative of that first. And I actually might write over on the side derivative of arcsine x, just so we can see that in front of us. That's going to be 1 over the square root of 1 minus x squared. Okay, so taking the derivative of the arcsine function, we're going to go 1 over the square root of 1 minus blah squared, where blah is our inside function. So we'll keep that the same. And then we need to multiply by the derivative of the inside function, which is 7. So to give our final answer, we would multiply the numerators together to get 7. And then we usually just expand out under the root to make that look a bit nicer. So we'd say root 1 minus 49 x squared. So in almost all of these problems, there's going to be a chain rule because there will be usually something more than just an x inside our inverse trig function. It will usually be like 7x or x squared or something like that. So we'll watch out for that. So now our function is 1/3 arcsine of x over 4. Let's find f prime of x. So the 1/3 can just hang out in front. We're going to take the derivative of the arcsine function by going 1 over square root of 1 minus blah squared, where blah is our inside function, and then multiply by the derivative of the inside function. So derivative of x over 4 is 1/4. Okay, now let's think about how to clean this up. So let's turn this into a single fraction. So the 3 can come into the denominator, the square root can come into the denominator. Under the square root, we've actually got 1 minus x squared over 16. And then we've also got this 4, this factor of 4 that's in the denominator. Okay, now one pattern that you'll see occasionally with these arcsine derivatives is we could take that 4 and we could instead think of that as root 16. And the reason why we might like to do that is because if you have one root multiplied by another, you can actually turn that into a single root. Remember that root a times root b is the same thing as root ab. The reason you might like to do that is because that's going to clear fractions for us. So we'd have 1 over 3 times certain square root. Just multiply the 16 through with everything under the first root, and you'd have 16 minus x squared. And it turns out that looks a lot better. So that pattern is going to happen anytime your expression inside the trig function has a fraction in it. You'll get that fraction coming out as part of the chain rule, and then you'll be able to rewrite the denominator there as a square root just to clean up the overall denominator of your answer. So it's not something to stress too much about. I mean, if you gave this line here as your answer, I would say, yeah, that's correct. And then if you were checking your work in the course pack, they would say this. So basically, we just want to be able to understand that these two things are equivalent and that you still got the right answer if you had said this version here. So now our function is x times arc cos of x squared. We're going to take the derivative. We're going to have a product rule here. X will be one of our factors, and the other factor will be the arc cos function. So applying the product rule, we'd have x times the derivative of arc cos of x squared. Okay, derivative of arc cos, might write that just over on the side for us to look at. Derivative of arc cos of x is negative 1 divided by the square root of 1 minus x squared. So it might be helpful just to have that on the screen while we're trying this derivative. Okay, so we're going to take the derivative of this guy here, the arc cos of x squared. We're going to get minus 1 divided by the square root of 1 minus our, whatever our inside function is, squared. And then according to the chain rule, we have to multiply by the derivative of the inside function, which would be 2x. And we're going to continue with our product rule. We're going to do this the other way around. So second factor arc cos of x squared times the derivative of our first factor, which is just 1. In order to clean this up, for the first term, let's multiply the negative x with the 2x to get negative 2x squared. That's all going on top. On the bottom, we've got square root of 1 minus x to the fourth. And then we just say plus arc cos of x squared. So now we're going to practice our derivatives of arctan. Might be nice to have the formula just written on the side here. So derivative with respect to x of arctan x is 1 over 1 plus x squared. So we're going to try to apply that formula here when we've got a chain rule going on, because we've got something more complicated than just the x that's being input into that arctan function. Okay, so let's think about our derivative. We'll deal with the arctan, or the outside function, first. So we're going to go 1 over 1 plus something squared, where something is that inside function, and then multiply by the derivative of that inside function. So on top, we'd have 1 times 2, which is 2, and then on the bottom, we'd have 1 plus 4x squared. For part E, our function is arc cos of the cube root of x. First thing you might like to do here is just do a rewrite and say that's arc cos of x to the 1/3. Might make it a little bit easier to apply the chain rule down the line. Okay, so let's think about our derivative. Our outside function is the arc cos function. So our derivative is going to look like minus 1 over the square root of 1 minus something squared, where something is our inside function. And then we need to multiply by the derivative of our inside function. So derivative of x to the 1/3, 1/3 x to the minus 2/3. And then from there, let's just think about how we would rewrite this. So on top, we just have a negative 1. The factor of 3 can go into the denominator. The x to the minus 2/3 can go into the denominator now as an x to the positive 2/3. And then we'd have the square root. Under that square root, 1 minus, and then this stuff here is going to be x to the 2/3. And if you like, you can just put a dot here to make it a little bit easier to read, to understand that it's 3x to the 2/3 times this square root of 1 minus x to the 2/3. So f of x is arctan of 8x minus 5x squared, all cubed. Now the arctan function is just applying to the 8x, could alternatively be written like that. But just to keep it simple, we're not going to have any brackets on here. So when we look at this expression, or this function here, it's good to realize that the outside function is the cube. So when we do our chain rule, that's what we're going to be starting with. We're going to bring that power of 3 down. Power is going to decrease. We'll keep our inside function the same. So we're going to recopy the arctan 8x minus 5x squared. And then outside, we need to multiply by the derivative of the inside function. So let's think about the derivative of arctan of 8x. It's going to be 1 over 1 plus our inside function squared times the derivative of that inside function. And then moving over to the next term, we'd have the minus 10x. So in terms of rewriting this answer, we would keep the first part as is. That looks good. There's no simplification that's going to happen here. So we've got 3 times arctan 8x minus 5x squared, all squared. And then let's concentrate on the stuff in the second set of brackets here. First thing you might do is just clean up that first term and then make that 8 over 1 plus 64x squared. So we've got that minus 10x. And the second thing you might do is just create a common denominator. I'll do that over a couple of steps here. Create a common denominator so that all the stuff in this last set of brackets here can just be written as a single fraction. So we would multiply that negative 10x top and bottom by the 1 plus 64x squared. And that way, things are going to look a lot nicer in the next step. So we'd have 3 times something squared, where the something is the arctan 8x minus 5x squared, so nothing's changing there. But now we no longer need this big set of square brackets at the back. We can just say that's times something over 1 plus 64x squared. And what do we have? We've got 8. And then if we multiply the negative 10x with those two terms there, we're going to have a minus 10x and a minus 640x cubed. So that allows us to get rid of the square brackets and just write everything a bit more nicely. So another way of rewriting this would just be to give it as a single fraction. You'd have 1 plus 64x squared on the bottom, and on top you'd have the 3. You might write the polynomial next, and then finally you would have the square of the arctan 8x minus 5x squared. So again, the point of doing this algebra here is just really so that you can compare answers with the course pack. So if you had written this stuff here up at the top, that's correct. You've taken all your derivatives, so technically you're done. And then the course pack might say something like this or might say something like that. So you just want to be able to confirm that if you gave this top version as your answer, that really is the same as writing it like this or writing it like that. So now we're going to try a derivative calculation where we actually evaluate our derivative at a certain x value. So we've got y equal arctan x over 1 plus x squared. And first thing we'll do here is we'll just find our derivative dy by dx. Once we've got that, then we'll think about plugging in. So we're going to do our quotient rule. We'll start with our denominator, 1 plus x squared. And then we need to multiply that by the derivative of the numerator. So derivative of arctan x is 1 over 1 plus x squared. And then continuing with our quotient rule, we're minus our numerator. So that's minus arctan x times the derivative of the denominator. So that would be 2x, and then that's all over denominator squared. So 1 plus x squared squared. Before subbing in, I would suggest we just do a little bit of simplifying. So what's really nice here is the 1 plus x squared and the 1 over 1 plus x squared multiply together just to give us 1. That's super nice. And then for the second term here, a little bit more natural to write polynomial type terms before inverse trig functions because it makes it easier to read. So 1 minus 2x times arctan x, and then on the bottom, 1 plus x squared all squared. So now that that's simplified, let's think about plugging in our x value. We're told in the problem that we want to evaluate dy by dx at the x value -1. So dy by dx evaluated at x equal -1 is equal to, well, we're going to have 1 plus, this is going to become a positive 2, times arctan of -1. And then on the bottom, we're going to have, well, if you take -1 and square it, that's going to become 1. So we've really got 1 plus 1, which is 2. Let's call it 2 squared. Okay, maybe let's think about arctan of -1. So arctan of 1 is going to be pi over 4. The way that we know that, we can draw our special triangle, which is the 1, 1, root 2 triangle. That's got an angle of pi over 4 up at the top here. And so you're asking, what angle has a tangent value of 1? So for which angle is opposite over adjacent going to be equal to 1? That's going to be this angle here, pi over 4. So arctan of 1 is pi over 4, and that means arctan of -1 is equal to negative pi over 4. So essentially this type of reasoning, you would want to be comfortable either doing that in your head or doing that very quickly over on the side. And then we can come back to the main flow of our calculation here. So we've got 1 plus 2 times negative pi over 4, and that's all over 4. So one thing you could do to make life a little easier is you could cancel a factor of 2 from the top and the bottom there. So we've now got 1 minus pi over 2 all over 4. But that still looks pretty awkward because we've got this double division where we've got a fraction that's being further divided by something else. So when that happens, we multiply top and bottom. If we multiplied by 2 over 2, that would make things a lot nicer. So multiplying the entire numerator here by 2, we'd have 2 minus pi, and then multiplying the denominator by 2, we'd have 8. So 2 minus pi over 8 would be our final answer there. This is our last problem. Let's say we're told that k is a constant, and we want to find the derivative of arctan of k over x. Well, let's say that derivative is equal to, okay, we're going to do our chain rule. So taking the derivative of the arctan function, you're going to get 1 over 1 plus something squared, just keeping that inside function the same. And then we need to multiply by the derivative of that inside function. So we need to multiply by the derivative of k over x. Well, for the sake of making things easier in the next step, maybe what we want to do, instead of saying k over x, let's say kx to the negative 1, because I think that will make taking the derivative a little bit easier. So we've got this 1 over 1 plus, we could call that k squared over x squared, if we want to write it that way. And then let's multiply by our derivative. So multiplying by, well, this k is a constant, that will just stay in front there. So we'll get negative k, and the power on the x is going to decrease, so it becomes more negative. Get negative k x to the negative 2. Okay, now for the sake of finishing the problem, we might want to put that back into the fraction notation. So instead of saying that, we might want to say minus k over x squared, because that's going to look nice when we do our final simplification. So what have we got on top? Let's multiply our numerators together. We've got 1 times minus k, which gives us negative k. And then on the bottom, the x squared here, we'll just multiply with all this stuff in the denominator. So multiply the x squared with all that stuff, and you get x squared plus k squared. So as usual, if you were writing a test or an assignment and you said this as your answer, I would say, yes, that's correct. But if you're doing homework and you were comparing your answer with the course pack, they're likely to write it this way. So we just want to be comfortable with the fact that those are the same thing, written 2 different ways. So that was review of inverse trig functions. We focused mainly on the arcsine and the arctan functions because those are the ones that come up the most in applications. And then we did derivative formulas for arcsine, arctan, and the arccos functions. Thanks for watching.